Hi, Assalamualaikum. We are from Group 1 and today we are presenting the aerodynamics performance analysis of side mirrors on vehicle track and weight condition. This study focuses on how different design of side mirrors affect the airflow around the vehicle, particularly their contribution to drag and weight condition behind mirrors. Before we begin, may I introduce our group members. Ahmad Danish, the team leader, Adif Huzaidi, the documentation engineer, Ahmad Amar, the design engineer, Madad Ashraf, the simulation engineer, and George Tanjahau, the simulation engineer too. In this study, we will analyze the velocity controls to compare the weight formation produced by both designs. We will also observe how the different design will affect the airflow accelerated around the outer spaces of the side mirrors. This analysis will help us understand how each different design of side mirrors will affect the flow field behind the mirrors and its potential to wake formation and the overall vehicle aerodynamics.
Assalamualaikum and good day everyone. First, I would like to explain the project background. Aerodynamics is an important part of vehicle design because it affects fuel efficiency, vehicle performance and carbon emissions. Although side mirrors are small components, they can still disturb the airflow around a vehicle and increase air resistance. In this project, we use computational fluid dynamics, or is known as CFD, to compare two different side mirror designs and study how their shapes affect airflow and aerodynamic performance. CFD is chosen because it is faster and more cost-effective than wind tunnel testing. Next is the problem statement. Side mirrors are an important safety feature because they help drivers monitor the traffic around their vehicles. However, their shape causes the airflow to separate as air passes around the mirror, creating a turbulent wake behind it. This turbulence increases aerodynamic drag, which means the vehicle needs more energy to move forward. As a result, fuel consumption and carbon emissions can increase, and wind noise around the side window may also become more noticeable, especially at higher speeds. Although many studies have shown that changing the shape or position of the side mirror can improve airflow and reduce drag, there are still limited CFD studies that directly compare different side mirror geometries under the same simulation condition. Therefore, this project aims to compare two different side mirror designs using CFD simulation to determine which design produces smoother airflow, lower drag, and a smaller wake region. Our hypothesis is that a streamlined side mirror design will produce lower aerodynamic drag and a smaller wake region than a conventional bulky side mirror. We also expect the streamlined design to provide smoother airflow around the vehicle. Finally, the objective of this project are to analyze the effect of different side mirror geometries on aerodynamic drag force and to investigate the wake formation and airflow behavior around the side mirrors using CFD simulation. That's all from me. Thank you.
For methodology, we imported both side mirror models into axis space frame. Then we got an enclosure which is the abdomen around each mirror. Both models are the same size but different shape. We use the larger dimension 42.45 millimeters for top and bottom, left and right. We multiply it by 5, which is 212 millimeters. For the front and back, we multiply it by 10, which is around 412 millimeters. For the front and back, we give more space because that is where the air flows in and out. Then we apply shear topology so that the mirror and air become one fluid region. Next, we make the mesh. We add the final size of 0.002 meters on the mirror surface for better accuracy. Then we name the boundaries. At the back end is the inlet and the front end is the outlet. The top, bottom, left and right sides are the symmetry. The mirror surface is the wall. We generate the mesh and save it. We did the same for both models. After that, we use fluent to set the physics. The inlet velocity is 30 meters per second, and the outlet is 0 Pascal. The fluid is air, and the mirror is no-slip wall. We choose the K omega as the turbulence model with a pressure-based steady solver. Then for solving, we use hybrid initialization and set the method to couple. We run the calculation for 400 iterations to solve the velocity, pressure, and turbulence. We check the convergence by watching the residuals and drag force become steady. Finally, for post-processing, we write the drag coefficient and we make the pressure contours, the velocity contours, and streamlines to see the airflow and the weight around each mirror.
Both models were simulated using the same CFD settings and converged successfully after 400 iterations. The scaled residuals and force monitor stabilize, indicating that the simulation results are reliable for comparison. The velocity contours show that Model 1 produces a larger wake region behind the mirror, while Model 2 has a smaller wake with faster flow recovery. The pressure contours also indicate that Model 1 experiences a higher pressure buildup at the front of the mirror, resulting in a larger pressure difference and stronger flow separation. The turbulence contours show that Model 1 has a larger and longer turbulent wake, whereas Model 2's turbulence dissipates more quickly. The streamline analysis also reveals that Model 1 forms two distinct wake regions behind the mirror, while Model 2 produces only one small wake region, indicating smoother airflow. Overall, Model 2 demonstrates better aerodynamic performances than Model 1. It generates a smaller wake, lower pressure buildup, shorter turbulence region, and only one wake formation compared to the two wake regions observed in Model 1. Therefore, Model 2 is the more aerodynamically efficient side mirror design.
To conclude this section, we observe that both models showed different flow behavior. In both cases, the airflow accelerated around the outer surfaces of the mirror before trailing at the edge, resulting in a low velocity wake downstream of the mirror. However, the characteristics of wake formation varies between the two designs. This analysis gives an invaluable insights for the side mirror aerodynamics performance improvement in future vehicle.